Assalamu Alaikum Rahmatullahi, Barakatuh. Today, this is the second video, and we are still going to study quantum mechanics. The topic which we shall learn about is about Compton Effect. Okay, Compton Effect. So, what is this Compton Effect? It is the scattering of photon by a charged particle, usually an electron, and what it results is that the scattered photon has less energy compared to that of the incident photon, and consequently a higher wavelength. Okay, so basically what happens, the experiment of Compton, which we shall describe now, was only possible due to the precise determination of X-ray wavelengths, which could be made using crystal spectrometer. Okay, so what happens here is that the light quantum, so let me draw the diagram for you. So this is the diagram of an incident photon. Okay, and it hits an electron which is at rest, and then after hitting it gets scattered, okay, in the direction. Okay, it makes an angle, say theta, with the x-axis, and the recoiling electron direction is this way. Okay, so that recoiling electron makes an angle phi with the x-axis. Okay, so let me write, this is the incident photon. Okay, this is the incident photon with say momentum p naught, and this is the scattered photon with momentum p1, and this is the recoiling electron with momentum p2. Okay, consequently the energy for the incident photon should be E naught, the energy for the scattered photon should be E1, the energy for the recoiling electron should be E2. Fine. So here, the light quantum imparts some of its energy to the electron and emerges with a lesser energy. So E1 is less than E naught. You should understand this. Okay, and consequently the scattered radiation has lesser frequency than that of the incident frequency. So the kinematics of the collision process can be worked out on elementary applications of the laws of the conservation of energy and momentum, which we shall do in a few moments from now. Okay, so the calculation gives us the following expression for the shift in wavelength, which is given by del lambda is equal to 2h by mc sine square theta by 2. So this is the result which we shall describe. This del lambda is called the shift in wavelength. Theta here is referred to as the angle of scattering. Theta is referred to as the angle of scattering of light quantum. Okay, now this diagram which you see on my right is the diagram of the intensity variation as a function of the wavelength of the scattered photon. Okay, so what happened here was that you should look this carefully. There are 4 diagrams, 1 2 3 4. Okay, in the first diagram, okay, we see that there is only one peak. Okay, and this peak is because of the fact that the photon may be scattered by the whole atom. Okay, so angle theta is equal to 0, so this is equal to 0, so that means the scattered photon is along the direction of the incident photon. Consequently, the M appearing here, okay, I remember I am talking for this part only. Consequently, the M appearing here, okay, should not be the mass of the electron, but it should be the mass of the entire atom. Okay, thus here the shift in wavelength is negligible. The second peak corresponds, you see, now we have different 2 peaks, 1 2. This is the original wavelength line, which is at 0.700 angstrom, which is lambda naught, which is lambda naught, as you can see in the video. This is the unaltered wavelength line. This second, from the second figure onwards, you have 1 2 3 and so on. This from the second peak corresponds to the Compton shift. In each figure, the 2 vertical lines, 1 2 like this, 2 vertical lines correspond to the unmodified wavelength and the modified. This is the original wavelength, as I told you, and this is the modified wavelength. Okay, as given by this equation, del lambda is equal to 2h upon mc sin square theta by 2, where h is called as a Planck's constant and c is referred to as the speed of light. Okay, so this is a brief introduction about this. Then let us try to derive this equation. Okay, but before that, some preliminary things we have to know. Know that the momentum of a photon is given by P is equal to E by C, and the energy of the, where E is the energy of the photon, and the energy of photon is given by E is equal to h nu by C, where nu is the frequency of the photon. Okay, so if we have our incident photon, which is given by P naught, and E naught is the energy of the incident photon, then how do you write? P naught is equal to E naught by C, which is equal to h nu naught by C. This is for incident photon. And for the scattered photon, we have P1 is equal to E1 by C, that is equal to h nu 1 by C, that is for scattered photon. Okay. Similarly, for this electron, just a minute, this is for photon. Similarly, for this electron, its energy is, when the electron is at rest, when the electron is at rest, its energy is equal to mass of the electrons times c square. Okay, now after it has been hit by this photon, we will assume that it is moving relativistically, hence its energy is given by, after collision, energy of electron is equal to m square c raised to 4 plus p2 square c square whole to the power half. So this is the energy of the recoiling electron. Okay, so now we have to derive this result del lambda. Okay, so del lambda is equal to 2h by mc into sine square theta by 2. So let us proceed. Let us look at this diagram. To this side, towards my right, we have the positive x-axis, and toward the upper end, we have the positive y-axis. Okay, so we have to use the law of conservation of energy as well as the law of conservation of momentum. Okay, so using the law of conservation of momentum. Okay, so look at the diagram. So here what we learn, vectorically we can write P naught is equal to P1 plus P2. Okay, P naught is equal to P1 plus P2, or in other words, resolving along the x-axis, what do we get? We get P naught. Okay, for the incident photon we have P naught only, and for the after collision events this side we have P1 cos theta plus P2 cos phi. So these are the thing we have. Okay, so let us write P naught is equal to P1 cos theta plus P2 cos phi. Okay, so you can give it an equation number 1. And similarly, if you resolving the y components, you see for the incident photon has no y component, so it is y component of momentum for the incident photon is 0, whereas for the scattered photon and recoiling electron you have the y components of the momentums, and that is what P1 sine theta, and for the recoiling electron its y-axis is in the downward direction, so you will have minus P2 sine phi. So write down resolving along the y-axis, what you have 0 is equal to P1 sine theta minus P2 sine phi. So this is equation number 2. Okay, so going to the next page. Okay, I have again redrawn the diagram here. So if you square and add the above equation, what do you get? You get is this one. Okay, P square, you get P2 squared is equal to P naught squared plus P1 squared minus 2 P naught P1 cos theta. So this is what you get. Okay, so just keep it for a while. Give it equation number 3. Now you apply law of conservation of energy. So remember, while deriving the Compton effect formula, you have to use two conservation laws. One is momentum conservation and energy conservation. So now using the law of conservation of energy, what do you get? You get E naught for the momentum, energy of the photon is E naught, plus the electron was at rest, so its rest energy will be mc squared is equal to energy of the scattered photon after scattering, that is E1, plus the electron after scattering moves relativistically, so its energy is given by m square c raised to 4 plus p2 squared c squared whole to the power half. So this is what is the using energy conservation, we have this. Okay, now you should know, prior to using this derivation, I told you that photon energy is given by E naught is equal to P naught into C, and E1 is equal to P1 into C. So please remember this, we are going to use this. So take this E1 to this side and mc square this side. Just a minute, E naught minus E1, okay, this E1 goes to the left hand side, plus mc squared is equal to, my aim is to remove this half, so I'll square on both sides ultimately, plus p2 squared c squared whole to the power half. Now using this result, just put it here, c into p naught minus p1 plus mc squared, that is equal to m square c raised to 4 plus p2 square c square. Now you remember, if you square on both sides, this half is removed, so you have this whole squared. So ultimately what you will have is this. So see, we have to use this value of equation number 3, p2 squared here. Okay, so I am going to use this value here, and see, at the same time I will expand all of this directly. So c squared into p naught squared, okay, plus p1 squared minus 2 p naught p1, okay, plus m squared c raised to 4 plus 2c p naught minus p1 mc squared, okay, that is equal to m squared c raised to 4. Now you use the value of equation 3 here, plus p naught squared plus p1 squared minus 2 p naught p1 cos theta into c squared, okay, from equation 3. Okay, I hope it is clear to you. Now everything is easy. Now everything has been simplified. So after simplification you can write 2, because you see p naught square plus p1 square c square will be cancelled with this, p naught square plus p1 square c square towards the right, so left hand side and right hand side, both of them will cancel out each other, and the remaining terms will be as follows. You see we have mc square, okay, so write down 2 mc square dot this 2 mc square dot c p naught minus p1, okay, so that is that one you can write nicely as minus 2c squared p naught p1, okay, this m square c raised to 4 and m square c raised to 4, it gets cancelled out, so what is remaining here is this this term, that is equal to minus 2c squared p naught p1 cos theta. Okay, so which you can simplify further and write like this. C square gets cancelled out, and 2 gets cancelled out. Okay, so ultimately which you can write is like this: MC 1 by, okay, so you can write it like this: P1 minus, that is equal to 1 minus cos theta. So this is what you can write. Let me verify it again. P naught minus P1 P naught, that is equal to, yes, I think yes, it is correct. So finally we have the result, and that is what? MC by P1 minus MC by P naught is equal to 1 minus cos theta. We shall again use one fact, that is what? This lambda naught is equal to H by P naught. Okay, lambda naught is equal to H by P naught, and lambda 1 is equal to H by P1. Okay, so please remember this, we are going to use them. So the shift del lambda is equal to lambda 1 minus lambda naught, that is equal to 2 times lambda c, called as the Compton wavelength, into sine square theta by 2, since 1 minus cos theta, trigonometrically it is equal to 2 sine square theta by 2. Okay, remember one thing, lambda 1 is the wavelength of the scattered photon, which is greater than the wavelength of the incident photon. Okay, so this is how, this is the diagram, and that is why you have this, where the Compton wavelength is H by MC. So remember this Compton wavelength. Hence we have this equation, famous equation called as the Compton equation, and lambda c is equal to H by MC is called as the Compton wavelength. Okay, the calculated value of 2 lambda c is equal to 0.04852 angstrom, and this very well agrees with the experimental value, which is roughly equal to 0.048 angstrom. Okay, now you should remember this. Hence you must remember one thing. So we have ultimately derived. Okay, hence you must remember one thing. That is, there is no Compton shift for light in the visible region. Okay, because the photon energy in this case is not large compared with the binding energy of even the loosely bound electrons. And please remember, the electron which we have considered here is the free electron or loosely bound electron. Okay, so that's all about the Compton effect, and that's enough. So please remember, I'm going to post regularly, so please keep an eye on my channel, and that's all. Thank you for watching.